So have you ever wondered how those massive nationwide surveys get done without completely breaking the bank? Well, a lot of the time, the secret sauce is a technique called one-stage cluster sampling. It's an incredibly powerful way to save time and money, but, and this is a big but, it comes with a really important statistical catch. So in this explainer, we're going to break down exactly how it works, when you should use it, and how to think about its trade-offs.
All right, here's our game plan. First, we'll cover the how, the basic formulas you need to get started. Then we'll jump into the practice with a GPA study, just to see it all in action. After that, we'll dig into the why of it all, comparing it to the simple random sampling you're probably used to. That's going to lead us to a super important idea called the intra-class correlation coefficient. And finally, we'll lock in our intuition by looking at two totally different artificial populations.
Okay, let's build this thing from the ground up. To keep it simple at the start, we're going to look at the most straightforward case there is, one-stage cluster sampling, where every single cluster is the exact same size.
First things first, you kind of have to flip your brain a little bit. With a simple random sample, right, you're picking individual people from one giant list. Not here. With cluster sampling, you are picking entire groups all at once. These groups, they could be city blocks, classrooms, hospital wards, whatever, are the things we're actually sampling. And we call them primary sampling units, or PSUs for short.
Now, if you're thinking, oh great, sampling groups means a bunch of brand new, complicated formulas, well, I've got some good news. Check out this table. The big idea here is that we're basically just doing a simple random sample, but not on individuals. We're doing it on the totals from our PSUs. Look at that formula for the total. You just add up the totals from the clusters you sampled, that's your sigma TI, and then you scale it up with that n/n factor, just like you would in simple random sampling. To get the mean? Easy. Just divide that big estimated total by the total number of people, which is just n times m. And the variance formulas? They follow the exact same logic. They're just driven by the variance of those cluster totals.
And this term right here, this S squared T, this is the whole ballgame. It is literally just the sample variance of the totals you got from your clusters. This one number is the engine that drives all the uncertainty in our estimates. The precision of our entire survey really just boils down to one question. How different are the totals from one cluster to the next?
Okay, that's enough theory and abstract formulas for a minute. Let's make this feel real. The best way to see how these pieces actually click together is to just walk through a practical example. So picture this. A student wants to figure out the average GPA in their dorm. Now, getting a full list of every single student to do a simple random sample, that's a huge pain. But they know the dorm has 100 suites, and every suite has exactly 4 students. So they just randomly pick 5 suites and survey every single person inside those 5. So here, n is our 100 suites, little n is the 5 we sampled, and m is the 4 students in each one.
And boom, the data comes in. We've got the individual GPAs for all 20 students. But here's the absolute key. For our cluster sampling math, we don't really care about those individual GPAs directly. The only reason we need them is to get the total GPA for each suite. You see that highlighted total row at the bottom? That is now our dataset. Those 5 numbers are all we need for the rest of the analysis.
Okay, so let's walk through it. First, we just take the average of our 5 suite totals. Easy enough. Then, we scale that up to guess the total GPA for the entire dorm. Next, we calculate our good old friend S squared T, the sample variance of those 5 totals. And once we have that, we can finally get our estimated mean GPA, figure out its standard error, and build ourselves a confidence interval.
And here are the results. Our best guess for the average GPA in the dorm is 2.826, with a standard error of about 0.164. Now pay close attention here, because this is a detail that trips up a ton of people. When we build our confidence interval, what are our degrees of freedom? It's not 19 from the 20 students we talked to. Nope. It's based on the 5 suites we sampled. So we use 5 minus 1, which is 4 degrees of freedom. This is a huge reminder that in cluster sampling, your real statistical power comes from the number of clusters you sample, not the total number of people.
And of course, in the real world, you're going to use software for this. In R, if you're using the survey package, the magic happens in that IDE argument. By telling the software IDE equals to suite, you're explicitly saying, hey, suite is my primary sampling unit. That one little command makes sure all the means and standard errors are calculated the right way, accounting for that clustered structure.
All right, so we've got our estimate, but now for the million-dollar question every survey designer has to ask. Was this a good design?
I mean, how did its precision stack up against just taking a simple random sample of 20 students from across the whole dorm?
Well, to answer that, we've got to look under the hood at the variance for both designs. On the left, you can see that the variance for our cluster sample is driven by something called the mean square between, or MSB. Just think of MSB as a measure of how spread out the averages of the different clusters are from each other. And on the right, you've got simple random sampling, where the variance is just driven by S squared, the good old overall variation among every single person. The whole question of efficiency just comes down to which of these two is bigger.
So it all boils down to this one simple comparison. If the variation that exists between your different clusters, your MSB, is bigger than the overall variation in the population, S squared, then your cluster sample is going to be less precise. It's going to have a higher variance than a simple random sample of the exact same size. This always happens when your clusters are really different from one another.
You know, this whole idea that it's all about the variation within clusters versus between them, that leads us to one of the most fundamental concepts in all of survey sampling. We need a way to actually put a number on this, to measure how similar or homogeneous things are inside our clusters.
So how do we do that? How do we quantify this idea of sameness inside a cluster? Is there some metric that can tell us if students in the same dorm suite tend to have more similar GPAs than any two students chosen at random from the whole dorm?
Yes, there is. It's called the Intra-Class Correlation Coefficient, or the ICC. And really all it is a single number that measures how samey things are inside the clusters. A high ICC means that if you grab two people from the same cluster, they're probably going to be pretty similar. A low ICC means they're not much more similar than any two random people you could have picked.
So, a positive ICC means people within a cluster tend to be alike. Think about it. People in the same neighborhood often have similar incomes, right? That's a positive ICC. And this is the most common situation you'll see in the real world. Unfortunately, it also means cluster sampling is less efficient than a simple random sample. Now, if your ICC is around 0, it just means your clusters are basically random handfuls of people. And if it's negative, which is super rare in natural groups, it means your clusters are actually more diverse than the population, which makes cluster sampling a great choice.
The design effect, or DEF, just ties this all together beautifully. It's just a ratio. The variance you got from your cluster sample divided by the variance you would have gotten from a simple random sample of the same size. And look at that little approximation formula, 1 plus m minus 1 ICC. It's so powerful. It tells you that the penalty you pay for clustering, your variance inflation factor, is driven by just two things: how big your clusters are, m, and how similar things are inside them, the ICC. Okay, to really hammer this intuition home, let's look at two totally fake extreme populations. We're going to use the exact same 9 numbers in both, but we'll group them into clusters in two very different ways.
Okay, look at population A. Each cluster is super diverse, right? It's got a low number, a middle number, and a high number. Each cluster basically looks like a mini version of the whole population. Now look at population B. It's the complete opposite. The clusters are incredibly homogeneous. All the low numbers are in cluster 1, all the middle ones are in cluster 2, and all the high ones are in cluster 3.
And when you run the numbers, man, it just pops right off the page. The contrast is just crazy. For population A, with the diverse clusters, almost all the variation is within the clusters. The mean square between is tiny, and that gives us a negative ICC. Now look at B. It's a perfect mirror image. All the action, all the variation is between the clusters, and that gives us an ICC that's almost a perfect positive 1.
And this right here, this illustrates the whole game. For statistical precision, for a good estimate, you want your clusters to be internally diverse, like in population A. You want each cluster to be a little microcosm of the whole population. When your clusters are just homogeneous silos, like in population B, picking one cluster tells you a lot about that silo, but it tells you nothing about the others. And that makes for a terrible, inefficient design.
Which, of course, brings us to the final critical question. If cluster sampling is so often less precise, why on earth is it one of the most popular methods out there? And the answer has absolutely nothing to do with statistics and everything to do with money and logistics. Think about it. It is way cheaper to interview 20 people in one single apartment building than it is to interview 20 people scattered all across the city. So in the real world, we are constantly making a deliberate choice. We trade away a little bit of statistical precision to gain a massive amount of practical, cost-saving efficiency. Understanding that trade-off, that's the key to being a smart survey designer.